I will start with a motivating example. The example of, first I'll tell, of course, the foundational work is joint work with Peter Grunwald, who was my PhD supervisor, and Wouter Kolen. Then I will tell you about a multiple testing project with my PhD student Yuri and with Jelle. And the slide I just made it this morning is a very recent work, and I think a very, very exciting result in multiple testing that we did with Jelle Groenman and Aldo Solari, who you might know from if you know something about multiple testing, from the revolutionary paper about simultaneous false discovery proportion results from 2011. And now we have similar results for false discovery rate. So I made the last slide about that. So first I will give you a motivating example and an example about how you can interpret these e-values with a simple coin tossing, a sequential coin tossing e-process. Then I will give you proper definitions of e-values, e-processes, what is exactly multiple testing and how do they combine. Then I will tell a little bit about the work with Yuri and Jelle that we put on arXiv in February. So there is one problem that appears when using e-process for multiple testing. We also have we don't have a conjecture, we have a proposition by now. And a solution to that problem, and then I fit in one last slide about our FTL control results with the e-values. So first the coin tossing. So let's say we want to test whether a coin is fair or not. And we are going to do a game of betting. So we start with a capital. This is not the coin that we're testing. This is our starting capital. And we start with a starting capital of €1. And now we will bet on the next outcome. So the next outcome might be heads or tails. And we will bet a fraction of our existing wealth on the coin being heads and tails. And if the coin has a bias, we can on the way learn the bias of the coin and then bet more money on either heads or tails, and we can become rich. And this is the whole idea of the e-values. You bet hypothesis. You start with one, and then you bet fractions of your wealth on the alternative hypothesis. And if you can become rich, this is an indication that the null hypothesis is not true. So let's do this. So let's say we bet 20 cents on that the next outcome will be heads. Okay, the next outcome is tails. So we give this a score of -1. So if it's tails, we say -1. If it's heads, we say +1. Well, then our wealth at the next time point 1, is our wealth at time point 0, L0 times this sum. So 1 plus the fraction that we bet, 20 cents, times the real outcome of the coin. So we encode a plus fraction of our wealth as we bet on heads and a minus fraction as we bet on tails. So now we bet 20 cents on heads, so then lambda 1 is 0.2. So you see that if we guessed in the right direction, we should gain some money, and if we guessed in the wrong direction, we should lose some money. So indeed, we now lose money, 20 cents. So now at time point 1, we have a capital of only 80 cents. So we do this again. Now we bet 40% of our wealth on heads, and it turns out to be heads. So we encode this with a +1, and then you see that we gain some money. So this is this 40%, 0.4 times +1. So now we have a capital of 1.12. And we can do this again and again. And if we write this down in a formula, what happens with our wealth at time point 2, that's this product. And the nice thing about this product is under the null hypothesis that there is no difference the coin is not biased. So we don't expect to have more heads or more tails. Under this null hypothesis, this thing is a stochastic process. And this is what we call a non-negative martingale. So it's a martingale that only takes positive values. And it has some nice properties. So one of the nice properties is that at any stopping time t, so we may stop when we wish. We may stop the process when we wish. When we think, oh, we are becoming rich, we can continue, or we can stop because of some outside reason, or we can continue because we have some more money. It doesn't matter as long as it's a valid stopping time. Under any stopping time, we have that the expectation under the null hypothesis is 1. This is just Dup's optional stopping theorem, which means that we do not expect to become rich if the null hypothesis. And we have a very powerful result due to Jeanville, which says that the probability that there exists a time, in the natural numbers that our martingale or stochastic process exceeds 1 over alpha is bounded by alpha. So it means if we set alpha to 0.05, which is what a lot of people do in applied sciences, then the probability that our martingale grows larger than 20 is bounded by 0.05. So that means that we have some sort of type 1 error guarantee. But note that this holds for any time n. So the probability that our stochastic process will ever exceed 20 is bounded by alpha. And just to show you what happens if you do this with p-values, if you compute the p-value and you look at the results and you go to the next p-value, you can prove that the probability that there exists a time that your p-value is smaller than alpha. So you find a small p-value. This is, of course, needs to be smaller than alpha, sorry. So the probability that you find a p-value that is smaller than your significance level that you set up front, if you do this optional stopping, is 1. So if the null hypothesis is true, there's no discovery to be made. If you do optional stopping with p-values, so you do this sequential game, then you're guaranteed to find a significant p-value. And it's even worse, it will become smaller than your alpha infinitely often. Yeah, so this LT is a non-negative martingale, and we have a generalization of that, and something that's slightly more general than martingales, and that is an E process. We'll give a definition in a minute. And it measures evidence against the null hypothesis. So you can really interpret it, if it becomes large, it's really evidence against the null hypothesis. And on top of that, you have this type 1 error guarantee. Okay, so now I will give proper definitions of everything, of both E processes and multiple testing. So one example, a motivating example, is multiple testing. For example, in neuroimaging, you can make a scan of a brain of someone, and then this brain is divided into about 130,000 voxels. And for every voxel, you basically do a hypothesis test. Is there activity in this voxel, or is there no activity in this voxel? So we are doing 130,000 hypothesis tests at the same time. And the core of the things that I'm working on is bringing flexibility and interactivity to hypothesis testing and to multiple testing. So typically what researchers want to do, they want to work in some way interactively with the data. So they want to, for example, to first analyze 5 patients and then look at the results and then determine whether it's promising enough to add another set of maybe 5 patients. Not possible with the classical methods. So that's one way that e-values and e-processes are going to help with this. And another dimension is that they might want to look first at the results of the whole brain to determine what areas are interesting, so what subsets of hypotheses are interesting, and then zoom in that and get error guarantees or numbers of the discoveries for that particular region. For example, in the brain, you have some clear anatomic regions, and it might be that the researcher wants to look at the data and then zoom in on some structural anatomic region. So with this project that I'm doing with my PhD students now is that we try to bring these 2 dimensions of flexibility into hypothesis testing and into multiple testing in particular. So let's make it a little bit more formal. So we just assume that there is some probability distribution or some distribution, P star, that's generating the data. And we wish to test a null hypothesis. That P star is in some set of probability distributions of some sample space. So again, for the t-test, this could be all Gaussians with mean 0. And often, but not always, we test the null hypothesis in contrast with an alternative hypothesis. And that's then that P star is in some other sets. For example, all Gaussians with mean non-zero on the same sample space. And now the definition of an E variable is that E variable E, to be very precise, for P, so for a set of probability distributions, is a non-negative random variable, satisfying that its expectation under every distribution in the set of distributions is bounded by 1, is at most 1. So if the data really comes from one of the distributions in this null hypothesis, then we do not expect E to become large. And in particular, we do not expect it to become larger than 1. So this is an E variable. Often people call it E value now, just as P values are also random variables. So there are some people that call P values P variables, to be precise. But as everybody calls P values, nowadays a lot of people call them E values as well. But it's a random variable. And with these E variables, we want to do a test. So we can, of course, define this more generally, but if we restrict to binary tests, we have a 0 or 1 valued random variable. And then the type 1 error of a test is the expectation under the null test. And we say that the test has level alpha if its type 1 error is at most alpha for every distribution in the null hypothesis. And then we have Markov's inequality for E variables, which is very nice. That says that if we have an E variable E for some null hypothesis, we have that the probability that E exceeds 1 over alpha is bounded by alpha for all distributions in the null hypothesis and for all alpha. So the indicator whether E is larger than 1 over alpha is a binary test of level alpha. So if we get an E value that's larger than 20, we can reject the null hypothesis at level 0.05. And Veal's inequality is just a sequential version of this. And now to the E processes. This is in the framework of anytime valid inference. That's the term that is now accepted for a new paradigm for sequential testing that allows the statistician to stop at any arbitrary stopping time that you don't have to specify in advance. So you might know that if you work with p-values, you have to specify the stopping rule in advance for the p-values to be valid, so to get your type 1 error guarantee. So you need to say either we stop after 100 subjects and that's it, and you cannot do anything else. There are also constructions in which you, for example, spend your alpha and you may look a couple of times in between, but generally you have to specify the stopping rule in advance. But here you don't have to. So if you have a research and it looks promising, and you think, this might be something, but my e-value has not reached 20 yet, and I really want that. And you go to your boss and you say, do you have some more money for 10 more subjects? And your boss says, yeah, sure, okay, go ahead. Then you can change your stopping rule, and you can also just stop because the weather is nice. So that's the framework of anytime valid inference. And e-processes, which is I'll come to that in a minute, are the central object for anytime valid inference. And by that, I really mean that you can show that every method for anytime valid inference must be based on e-processes. One thing in working with stochastic processes, so e-process is a stochastic process, is that you need to take care of the filtration that you're working with. I skipped the details. I guess you might know that. you need to make sure that the stopping time that the stopping rule that you're using is adapted to the same filtration as your e-process is defined on. So what's an e-process? An e-process is a non-negative process that satisfies that its expectation under any distribution in the null hypothesis for any stopping time is bounded by 1. So an e-process is just a stochastic process that for every time that you can stop, its expectation does not exceed 1. And there are equivalent definitions of that in terms of test martingales. One intermezzo, why are filtrations important? So in one of our papers, we have an example of that. So in the t-test, you generally work with an effect size, which is the mean divided by the variance. And in that way, you sort of take the scale, which is a nuisance parameter. You are interested in what is the mean of the Gaussian, is it 0 or not? But you have to somehow account for that extra parameter, the variance. So we call it a nuisance parameter. And one way to do with that is just to divide it out. So to say that you're working with a test for which the scale does not matter anymore. And so there are different filtrations that you then have. You have the full data filtration that does take the scale into account, but you can also define e-processes on a coarser filtration. So also a filtration that is ignorant of the scale. And if you can define in a certain sense, optimal e-process on that coarser filtration. But this e-process is then not an e-process with respect to the finer filtration, the full data filtration. And we showed that then if you use a stopping time that uses the scale of the data. So here the stopping time is, we see whether the absolute value of the first data point is in some specific interval. Then you see that the expectation is larger than 1. So it's not an e-process anymore. And all these type 1 error guarantees don't hold anymore. So I already showed Veal's inequality earlier. This is just an equivalent formulation of Veal's inequality. So the probability that exists a time and a time t that the e-process exceeds 1 over alpha is bounded by alpha is the same as saying that it holds for the most difficult distribution in the null, and then take the supreme over all times. And this is something that we will use very soon. And then, of course, we can ask ourselves the question, and this was one of the main questions of this safe testing paper from 2019, which, by the way, published in 2024, so that took a long time, but it was nice. One question that one could ask is then, what is a good e-variable? Because remember the definition, its expectation under the null should not exceed 1. So the e-variable that's always 1, irrespective of the data, is also a valid e-variable with your type 1 error guarantee. But of course, it's totally useless for hypothesis testing. So we want something that grows fast when the null hypothesis is not true. Or maybe we can formulate it as if there is an alternative hypothesis, we want an e-variable that grows very fast if the alternative hypothesis is true. And we formulate this in the grow criteria. We can do growth rate optimal or growth rate optimal in worst case. I'll focus on the worst case now. And that is the e-value E star that achieves the maximum over all e-values such that E is an e-value. So you have your type 1 error guarantee of the minimum of all distributions in the alternative hypothesis of the expectation under such a distribution in the alternative of the log E. We could also do E, but we have many good reasons for choosing the log as a transformation function here. One of them is that we then get exponential growth rates, but another one is that if you just take E or a polynomial of E or something like that, you can at some point lose all your capital. And one of these benefits of e-values is that you can work sequentially, but also combine e-values from different experiments. And if you work sequentially, but you lose your capital at some point, then there's nothing you can do anymore. No matter how nice the data are, no data can can multiply a zero to something else. So we do not want to lose all our capital, and that's the log. Taking the log prevents this. And then this is the main result of the safe testing paper, and this is how this all started. So this was basically the first way of constructing meaningful e-values for problems with composite null hypotheses. So this is the main theorem, and the main theorem consists of three points. The first point says that it exists. So this growth rate optimal in worst case e-variable exists for composite null hypotheses. And it satisfies some equations similar to what I just showed. Then this infimum from the first line is attained by some sort of generalized likelihood ratio, which takes the simple form. It is one distribution divided by another distribution. Z is the data, and this has the form of two base marginal distributions. So it's the integral of the distribution where the parameter is integrated out with help of some prior, and then the same for the null hypothesis. And then point, the third one, is that they can be found by a problem of doubly minimizing a KL divergence. And since the KL divergence is convex in both arguments, this makes it a sort of practical convex optimization problem to find these grow e-values. I must say, so it's not that practical, because if you have an infinite parameter space, you still need to find a suitable grid to optimize over, and this gives rise to a lot of complications. But yeah, in its basis, it's sort of elegant and sort of practical. Then I will go to the multiple testing bit. So a quick introduction. I'm sure many of you have seen this before. If we test n true null hypotheses at level alpha, then on average we will, of course, falsely reject alpha times n of them. And if n is in the 100,000s, this is a big problem. We don't want to end up with so many false discoveries. So these are some examples. So in multiple testing, we need other types of measures of acceptance or rejection errors. And we need statistical procedures how to control these measures of errors. So the goal of a multiple testing procedure is to come up with some collection of hypotheses that we want to reject. And we often call them discoveries. And just as with single hypothesis testing, we can make two types of errors. So type 1 errors, or not reject a false hypothesis, so type 2 errors. And here is a table where we denote the number of them. So the total number of the important bits to remember is V and R. V is the true hypotheses the number of true hypotheses that we reject, and R is the total number of hypotheses that we reject. And then a lot of paradigms in multiple testing consider some aspect of the false discovery proportion, and that is the number of true hypotheses that we falsely reject, V, divided by the total number of rejections, if that's 0, and if we reject anything, and if we don't reject anything, it's 0. So the proportion of false rejections among the total number of rejections. And in general, the set of discoveries is random. So both V and Q are random variables. So we must focus on aspects of their distribution. And these are the two, would say, most common paradigms in multiple testing. The family-wise error rate, which is that probability that we reject, that we do any false discovery. So the probability that we reject a true null. And the false discovery rate, which is the expectation of the false discovery proportion. And this, for example, FDR has been invented by Benjamin and Hochberg in the 90s. And they also proposed a method to control the false discovery rate, so the expectation of the false discovery proportion, which is now called the Benjamini-Hochberg procedure, the BH procedure. And in 22, Wang and Ramdas proposed the EBH procedure, and that goes as follows. So first we order the e-values from the largest to the smallest, and then we reject the k star largest e-values, where k star is the largest k for which we have that k. So the order of the e-value times ek divided by the total number of hypotheses, big K, exceeds 1 over alpha. And they show that this controls the false discovery rate. But the interesting part about this is, because this is somehow just inverting the standard BH procedure, the interesting part is that the standard BH requires some complicated assumption on the structure of the p-values, PRDS, positive regression dependence on the subset. And the nice thing is that if you, the proof is very different for e-values. And the nice thing is that you don't require this assumption. So this procedure, this EBH procedure, controls the FDR at level alpha, even under unknown and arbitrary dependence between the e-values. So that's nice. And you can see that you can show that BH and BY are special cases of EBH. Okay, and now I want to add a layer of flexibility to the multiple testing. So I want to work with e-processes for multiple testing. So we started that with my first PhD student, Yuri, 1.5 years ago, and we ran into a problem. And I will now show you what. So suppose that you have an e-process. So at time point 1, you have E1, and time point 2, you have E2, etc. And suppose that we already have gathered ET plus 1 before that we have evaluated the e-value from the time point before. And now, if ET is larger than 1 over alpha, but ET plus 1 is smaller than 1 over alpha, we can still go back to ET and reject the null hypothesis, because Veal's inequality states that we can take the supremum over all these time points. So we have not lost any evidence by gathering more data. We can go back. We can go back into the history and reject the null hypothesis anyway. But what happens if you do that with multiple hypotheses? So let's focus on EBH, but we can show this for other multiple testing procedures as well. Consider that we have k parallel e-processes. So for hypothesis 1, we have E1, E2, etc. And for hypothesis up to hypothesis big K, we have E1, etc. And then you can show that EBH guarantees that if we take the supremum over time of the FDR of these e-processes is bounded by alpha. Now consider that we have 2 hypotheses. Then you can see that EBH rejects any hypothesis for which alpha, and both hypotheses if both e-values exceed 1 over alpha. Now suppose that at time t, we have that E1t is between 1 over alpha and 2 over alpha, and E2t is smaller than 1 over alpha. Okay, so let's see, do we reject anything? We don't reject E1 because it's not larger than 2 over alpha. We don't reject E2 because it's also not larger than 2 over alpha. And we don't reject both because they are not both larger than 1 over alpha. So we don't reject anything. Okay, now we gather some more data. And now we have that E1 t plus 1 is smaller than 1 over alpha. And E2 t plus 1 is between 1 over alpha and 2 over alpha. So again, we don't reject anything because they are it's not the case that either of them is larger than 2 over alpha, and it's not the case that both of them are larger than 1 over alpha. But if we would have not gathered a data point for E1, then we would have rejected both hypotheses, because at time point t, E1 was larger than 1 over alpha, and at time point t plus 1, E2 is larger than 1 over alpha. So we have gathered data, and therefore we have lost our ability to reject both hypotheses. So we regret having gathered one more data point for e-processes for hypothesis E1. I think that's a problem. So as I said, EBH guarantees that if we take the supremum over time of the FDR of these E processes is bounded by alpha, but actually what we would like to control is the FDR of the supremum of all these E processes. Then we don't have this problem. And we would like to argue that this is the proper FDR criterion if we work with E processes. Note that you can also show this for other types of multiple testing procedures. Okay, if we work with the running maxima of the E processes, this problem of regretting having gathered more evidence is gone because the E process will never become smaller again. So yeah, we obtain a non-decreasing sequence of sets of rejected hypotheses of discoveries. But a problem is, of course, that the running maximum of an E process is not an E process itself. So we cannot straightforwardly prove FDR control. And but on the upside, if the E processes are independent, we have that 1 divided by the maximum processes are valid, P processes. And then therefore, so P sort of E value equivalent of the P value. For a P process, you have type 1 error control, again, for every stopping time for if you do it sequentially. So we have valid P processes, and then we can obtain FDR control via classical Benjamini work. So there is some escape. If they are independent, it's good. But if they are not independent, then we would like to inherit the arbitrary dependence from EBH. But unfortunately, we can show that if we use this cumulative maximum procedure, so we use these maximum processes with arbitrarily dependent E processes, we do not control the false discovery rate at level alpha. I'll skip the proof. This is just an example for which we show that it doesn't work. A solution to this problem is to use something called an adjuster. So they were invented around 2010 for stock financial applications. It's basically a function that fulfills these criteria. And the nice thing is that if MTK is the running maximum of an E process, then the adjusted maximum process is also an E process. So that's nice. The adjuster sort of tunes down the E process, the maximum process, such that it is an E process after all. And that's nice. And since the adjuster process is non-decreasing, and we started out with this maximum process, which was non-decreasing, it will never result in this problem of regretting having obtained more evidence, more data, having collected more data. So this is a solution. Of course, it has a downside, and that is that our adjusters are quite conservative, and there are many of them, and some are better in the small sample regime, and some are better in the high sample, a lot of samples regime, and it's still very unclear which one you should choose. And of course, you cannot try all of them and take the maximum. That would be nice, but that doesn't work. And we show that the adjusted running maximum process has FDR sup, so the new FDR criterion that we think is appropriate for working with E processes. That's bounding by pi naught. That's the fraction of true hypotheses times alpha. Skip the details. And then we have an informal theorem that if you want to use such a function, we have a theorem, and here is the informal statement of it. If we want to use such a function, tune down the maximum process, it needs to be an adjuster. Of course, if you want to have an increasing function, but we want to have that because we use the maximum to have a non-decreasing process to start with. Good. Then I have time for one super exciting thing that we have been working on, and we put it on arXiv, I think 2 weeks ago. And that is the E-partitioning principle. well, yeah, we call it the e-partitioning principle. This is work with Jelle and Aldo. And yeah, this is the how you say it, the main aspects of it. So this new thing, the e-partitioning principle, is necessary and sufficient for FDR control. That means that any procedure that controls the FDR, including all these p-value procedures, Benjamini-Hochberg, SU method, Benjamini-Diacocelli for arbitrary dependent p-values, etc. All these methods, every method that controls the FDR, well, it controls the FDR if and only if it's a special case of this general e-partitioning procedure. And the nice thing about this e-partitioning principle is that with that we can get uniform improvements of most of the existing methods. We are still working on BH, Benjamini-Hochberg. It would be nice if we find a way how to improve that. We can already match it. We have, Jelle and Aldo have a paper where they show that BH is inadmissible, as in that there is a uniform improvement possible. It's called a tiny but uniform improvement. Yeah, we are still working on that. But another nice thing is that you can, just as with FDP bound, to get simultaneous control, you have a post hoc flexibility in choosing which hypotheses you find interesting. So think again of the brain scan. You can first, compute your statistics, your procedure, look at the results, and then you can zoom in on a specific brain region if you want, and look at those hypotheses only and get guarantees for those. And this simultaneity was not known for FDR until now. I don't think that maybe people even didn't know that it should be possible, but yeah, it's possible, and that's very nice. And the nice thing is then for BH we still don't have an improvement, is that we reject more hypotheses, but already having this simultaneity is very nice. Then also, if you don't let your E values depend on alpha, you can get post hoc flexibility in choosing alpha. So you can choose your significant level also after seeing the data and after computing your E values. You can also switch to family-wise error rate. And also something that has not been known for FDR up to now is restricted combination. So there are some logical implications between different sets of hypotheses. And you can do that with this principle as well. Very briefly, I just show you the principle. Maybe it's a bit much to explain it now considering time, but it's based on, it's called the partitioning principle, and that is based on that you partition your set of hypotheses in the equivalence classes of true nulls and false nulls. So you have a lot of partitions of that, the power sets of your set of hypotheses. We, by the way, show that there are feasible algorithms to compute the main procedures that come out of this principle. And the main theorem is that this procedure controls the FDR. If and only if your method, so your set of rejections, is in this this e-partitioning procedure. I realized that this sentence is also a very long. It's a very long paper, but I just wanted to give you a very quick teaser. Look up the paper and let me give another talk about this paper. So this is the paper, Ruhr, De Heide, Solari. And one interesting simultaneity was that it turned out that Neil Su, Lasse Fischer, and Aditya Ramdas were working on the same idea simultaneously. And now we have teamed up, and now we are writing a paper with the 6 of us. And we are going to submit it with the 6 of us. So the conclusion. I mainly showed you about the paper with Jure and Jelle about this carefree multiple testing. So we don't want to regret having gathered more data. So we have some solutions for that. I know that now in the US, some people are working on other ways than adjusters to work on this. So I'm curious to see what happens there. We argue that for FDR control, instead of controlling the FDR soup, as EBH is doing, by the way, EBH is hugely improved by the e-partitioning procedure. So that's nice. Maybe we should adjust it in this paper too. So we want to argue that we should control the FDR of the soup of the e-processes and not the soup of the FDR of the e-processes. And we can solve this by using adjusters. But adjustment is costly in terms of power. It's unclear which adjuster to choose. So there are some problems there. This is again the slide about the e-partitioning principle. Many opportunities. And there are also many, I think for all existing methods, this principle gives opportunities to improve those. And we already have many examples of those in our paper. Just the one bit that we really want to get before submitting the paper is to improve Benjamin Hoek work. Okay, so thank you, and feel free to ask questions.